Hello and welcome to another episode of Slam TV. I'm Professor Roger Yang. We've got a fantastic episode for you today. Today we're going to talk about logarithmic scale. Luckily for you folks at home, we have a special guest with us. He passes both the horizontal and the vertical line test. You need scientific notation to express his awesomeness. He's Professor Jay Cho.
Thank you.
Jay, how's it going, buddy?
Pretty good. How about yourself?
Not too bad. I think we're having an earthquake. Duck and cover! Whoa, dude, that was intense. Oh my God.
It wasn't too bad, Roger. It wasn't that scary.
How intense was that earthquake?
Let me just check. It says it's about 5.3. That's not that
5.3?
bad. Yeah.
You know, I'm an East Coast guy, so this earthquake stuff is really pretty scary. Oh my God, we're having another earthquake! Whoa, dude.
Roger, there's aftershock.
Yeah, that wasn't as bad as the first
it
one.
wasn't. Let me check. How bad was that? Yeah, it was only 4.0. Are you okay?
I mean, I'm from the East
shaken.
Coast.
Right.
From the East Coast.
Right.
This earthquake thing is kind of scary.
It is kind of scary.
Let me try to pull it together.
Concentrate.
Math.
All right. We can do this. We
I
can
got
do
it.
this.
Okay.
All right. Good.
What are we talking about today?
We're talking about logarithmic scale.
Logarithmic scale?
Yeah.
Hey, wait a minute. Don't we measure earthquakes with something similar to a logarithmic
Right,
scale?
sure. Like this 4.0, 5.3,
Uh-huh.
these are all measured by this thing called Richter scale. It's
Which
just
is?
one application of a logarithmic scale.
Oh.
Right?
Richter scale is logarithmic scale.
Exactly.
Cool. Well, that's perfect because that's exactly what we're going to talk about today.
Yeah.
So there must be some physical mechanism that they use to measure these earthquake intensities.
Right. You've probably seen it. It's called the seismometer.
Oh, yeah.
It's seen on
Seismometer.
TV, right?
I think so. There's just like wire that kind of hangs from the ceiling.
Right, and there's a pen attached to it.
Yeah, there's a pen attached to the end, and then there's
Right.
like paper that kind of feeds
Right.
through like this.
So what happens is when it shakes,
Uh-huh.
it draws little waves.
Oh, yeah.
So imagine there's like a small quake,
Okay.
and just gonna draw like small waves, right?
What's the smallest quake?
Oh, let me look it up. Doo-doo-doo. Yeah. Oh, 0.001 millimeter.
Dude, that's really small.
That's tiny. A millimeter is like your fingernail. Like a,
The thickness of your fingernail, right?
So a thousandth of that. So
Dude,
you
I
can't
can't
even notice it.
Yeah, you
Yeah.
can't even see that. What about
Right.
what about the biggest one?
Biggest one? Let's look it up. Oh, wow. It's huge.
How big
It
is
says it's like 3,162,277.66 millimeters. Do you even know what that is?
That's like just
I mean,
one
it's
little
literally-
wave, one
Right.
gigantic.
So that's
Ampli-
huge earthquake. Yeah.
What is this number? Is this is the height of the
Right. That's the
wave, or is it the length of the whole wave? or
It's
what
just
is it?
half of it because the amplitude is just half of the
Oh, okay.
entire thing,
Okay.
going back and forth. Yeah.
So we've got these really short waves and these really huge waves.
Right.
There's like a ton of spread.
Right. This is going to be kind of like not issue, but difficulty of describing how strong the earthquake is. So I have choice of calling it 0.001 earthquake versus 3.2 million.
Right.
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 But those are numbers that either really small or really big.
Right. Hey, can't we use scientific notation to express these numbers?
Yeah, exactly. Scientific notation will make it easier for it to describe those small numbers and big numbers.
All right. So describe to me how we can show me how we can describe each of these numbers using scientific notation.
So for example, 0.01, 0.001, if you use scientific notation, I can write that as 1 times 10 to the negative 3 power.
Okay. What about the that huge like 3 million something earthquake?
Right, 3 million something, if I were to use scientific notation, is about 3.2 times 10 to the 6 power.
Oh, okay. So
what we do is, instead of calling it 0.001 and 3 million something, we can just look at the exponent of the scientific notation. So the first one, the small one, exponent was negative 3. And the big one, the exponent is 6.
Oh, okay.
So if you give me the scientific notation, I look at the exponent, then I can already tell if it's like a small one or the big one.
Oh, okay. Because like negative exponents mean it's really small.
It's a tiny one, yes. If you have a 6 exponent, that means it's like, I already know it's going to be a big one.
I see. Well, what about the decimal part, though? If you just look at the exponent of the scientific notation, you ignore the decimal part.
See, I knew you were going to ask that.
Ah.
But however, we're going to use this function called exponential function, 10 to the x power.
10 to the x power.
Exactly.
What's so great about this 10 to the x power function?
You know, 10 is a number. We live in the decimal world, digit 10. You have 10 fingers.
Oh, yeah, I do have 10 fingers.
Right, you might have 10 toes.
Of course I have 10 toes. Anyways.
So these are the function. This is the function that we use a lot.
Uh-huh.
And this is very convenient to use.
Okay.
So we're going to use that. And another good thing about this function is this is one-to-one.
Can you remind our viewers of what one-to-one means again?
Sure. One-to-one function means for every output, it comes from only one input.
Oh, okay.
Right.
So
And
every
it
output comes from only one input.
Yeah, and then it has an inverse also. Right.
Ah. How do I know that this function 10 to the x is one-to-one?
Well, if you look at the graph of it, you use this test called horizontal line test.
Oh, I remember the horizontal line test. The horizontal line test says that a graph corresponds to a one-to-one function if every horizontal line intersects the graph at most once.
Exactly. By the way, like Roger, is horizontal? I always get confused. Is this horizontal? Is this horizontal? Which is the horizontal? I know.
Jay, what's your favorite city to visit?
Las Vegas.
You know when you're driving to Las Vegas,
Uh-huh.
and you go over that last mountain pass, and you're coming down the mountain,
Yes.
and you see
all
the
these
city lights,
yes.
and you see the horizon.
Oh yeah, the horizon.
The
horizon. So it
Horizon.
goes like this. Okay.
Horizontal.
Okay.
Horizon.
Okay,
Yeah.
I got it. I
Got
get it. Okay. Cool.
So let's look at that graph again.
Right.
When you look at this graph, if you just take any horizontal line, it's only going to intersect the graph at most once.
Right. It's
With
not
that-
going to go through twice.
It's
right?
not going to go through twice, because if it went through twice, that means that two different inputs would have the same output.
Ah.
But a one-to-one function each output only comes from one input.
Right. So if every horizontal line goes through the line at most once, that means there's only one input.
Yeah.
Exactly.
So it looks like 10 to the x is one-to-one. What's so great about one-to-one functions again?
Because if it is a one-to-one function, then we can find the inverse. There is an inverse function. And this is what you're going to
Ah, yes.
use.
One-to-one functions have an inverse.
Exactly.
What is the inverse of this 10 to the x function?
It's called a logarithmic function.
Logarithmic function.
Exactly. And that's why we're going to use logarithmic scale.
The logarithmic scale comes from the logarithmic function.
Exactly. Exactly.
OK, so how does this thing work then?
Right. So what we try to do is we're actually interested in the exponent, 10 to the some power, right?
Right.
So what we do is we measure the amplitude.
Those are the heights of the waves.
Exactly. And I want to try to find out 10 to the what power will give you that number.
So the smallest earthquake was 0.001.
Right. So the question is 10 to the what power will give you 0.001.
Ah. The biggest earthquake measured, what, around
About
3.2 million?
Yeah, so in order to find the scale for that, it's like 10 to the what power will give you 3.2 million.
Oh, OK.
Right?
Why don't we,
Try to
take our calculator, plug that in, and see what comes
Okay.
up? So it looks like you want to plug 0.001 into the logarithm function.
Right, and as a result, you're going to get negative 3.
Oh.
What that means is 10 to the negative 3 will give you 0.001.
Ah, that
Right.
makes sense. And what about when you plug that 3,162,277.66 into the logarithm function?
Well, then you get 6.5 as an answer. What that means is 10 to the 6.5 will give you about 3.2 million.
I gotcha.
Right, right.
You know, I don't love the fact that that negative is there, that negative 3.
I knew that. Most people don't. Like, who likes negative, So what we're doing is we're just going to shift everything by 3.
Okay.
So negative 3 becomes 0, and everything else is just increased by 3.
And how does the logarithm function reflect that change?
Right, so when you actually calculate it, instead of taking log of the amplitude that you measure, we're going to divide the amplitude by 10 to the negative 3 power, which is 0.001.
And this is how the Richter scale works?
Exactly. So in real life, when you measure the 0.001 amplitude, we'll divide that by 0.001, divide by 10 to the negative 3 power. Take the log of that. As a result, you're going to get 0.
Ah. That makes sense. You want the smallest possible earthquake
Right.
to have Richter scale reading 0.
Exactly, exactly.
What happened about that 3.2 million amplitude?
The crazy one?
The crazy one, yeah.
So again, when you calculate it, 3.2 divided by 10 to the 3 power, you calculate that, take log of that. As a result, you're going to get 9.5.
9.5.
Yes, that's pretty intense.
Actually, I think I saw online that the largest earthquake ever was in 1960 or something in Chile.
Pretty scary.
That was the 9.5.
Pretty scary.
one.
Yep.
Well, what about the earthquakes that we had at the beginning of the episode?
Oh, see, I knew you were going to ask me. So I already contacted Detective Dr. Richter of the Kareem.
and what
he
did
just sent me a data. Let me just look it up.
From his personal seismometer?
Exactly, that he keeps in his backyard.
Oh, okay.
Oh, he said that the first one was 199.5 millimeters.
Okay.
And the second was 10 millimeters.
Oh, all right. Can you lead us through the Richter scale calculation of these two amplitudes?
Right. The first one, so you take 199.5, divide by 10 to the negative 3 power, and take the log of that. As a result, you're going to get 5.3.
Oh, okay. What about the second one?
Second one is 10, divide that by 10 to the negative 3 power, calculate that, take the log of that, and as a result, you're going to get 4.0.
Okay, so the first one was 5.3. The second one was 4.0.
Exactly.
I get it.
Exactly.
I get it. Yeah, this isn't so bad.
It's not that bad.
No.
Are you still scared of earthquake?
Heck no, I can measure that. Well, this concludes our episode. Thanks for watching.
Well, that's about Richter scale 1.5.